So we are now in the fourth unit of this course, and it's called The Wave Nature of Light. And that may give you a hint that what we're going to be looking at here is that light is a wave. We're going to talk about how that understanding came to be. But we'll also look at some interesting aspects that end up bringing us to that bridge us nicely to our Unit 5, which is about modern physics and quantum mechanics. So our first lecture is on the properties of waves and light. A lot of this will be review for you from grade 11 and some from grade 10. This is section 9.1 from your textbook. So we'll start off here just with an idea of waves. So it says, if you've ever gone surfing or you watched a news report about a tsunami, you know that waves can transmit a large amount of energy. Other examples of waves are mechanical waves, such as a wave on a vibrating string or the surface of a ringing bell, radio waves such as AM and FM waves, and seismic waves produced by earthquakes. All waves share the same basic properties. So we have very different types of waves, but a wave itself transmits energy. So it's the movement of matter, and through that movement of matter we have a transmission of energy. So we're going to go through a number of different terms that you should know, and what I would suggest you do is write down a definition for each of these highlighted words and copy down some pictures to help you understand it as well. So a wave is a moving disturbance that transports energy from one place to another, but does not necessarily transport matter. That's what I was kind of saying earlier. When we have a water wave, the particles of water are moving up and down themselves as the wave transmits, but it's not necessarily the water that's moving, it's the energy that's moving through the water. The front edge of a wave is called a wave front, and we can imagine this in two ways. If you look at that image there on the left, we have our wave fronts as the crests of some waves that appear to be linear on a water surface. If we drop something that causes in a flat surface and it causes a wave source, that initial disturbance will cause this wave source, and then we'll have the front of the wave front will be at the crest of each of the circular waves that kind of radiates out. And I used the word crest already, so that's the upper half of the wave, and trough is the lower half of the wave. So a crest is when the wave is above the equilibrium point, and a trough is when the wave is below the equilibrium point. When we have a complete crest and trough pattern, that is a cycle of the wave. So a wave cycles every time it goes from crest to crest, trough to trough, or basically when it covers an entire trough and an entire crest. The wavelength is the distance between two successive points that are vibrating in phase. So wavelength is the measurement of one cycle, and that can be measured from crest to crest, from trough to trough, or from the I guess the full length of one trough and the full length of one crest. The amplitude is the maximum displacement of the wave from its equilibrium position. So its equilibrium position would be where it is if no disturbance occurred. It will have a maximum displacement above that, and will have a minimum, or I guess a maximum displacement below. The distance from the equilibrium to the maximum or the minimum is the amplitude. So the period of a wave is the time required for one wave cycle to pass a particular point, and we measure period in seconds. The frequency of the wave is the number of wave cycles that occur per unit of time, and we usually say per second, so we use the units of hertz. So I'll talk about period and frequency. I guess I should also mention that they are reciprocals of each other, so the frequency is equal to 1 over the period, and the period is equal to 1 over the frequency. So period is basically the time of a cycle is our period, But frequency is the number of cycles we have per second. So if we have a number of different wave cycles per second, that's our frequency. Next, we have the universal wave equation. So the universal wave equation is V equals F lambda. So that is our velocity of our wave, how fast our wave is moving, and it's equal to the product of the frequency times the wavelength. So that gives us our, that relationship is our universal wave equation. We could also think of this as V equals lambda over the period, so the wavelength divided by the period. But really, you could always kind of derive that yourself on a test or on a quiz or when you're doing your homework. You have the universal wave equation on your formula sheet, although it's written with C instead of V. We'll get into that on why that is a bit later, but just remember that when you're using the universal wave equation, V, it's always V equals F lambda. And if we have something that's moving at the speed of light, a wave that moves at the speed of light, it would be C equals F lambda. So just a quick little explanation here. So what determines the frequency of the wave? And if you imagine that rock dropping inside of a calm surface of water, it's the initial disturbance that causes a vibration. So even as I'm speaking, the initial sound that I make, the initial cause of the vibration of my vocal cords, is what causes that frequency. The speed of the wave is determined by the frequency and the wavelength of the wave. So our frequency is determined by that rate of vibration, and the wavelength, depending on how something or how a source is developed, it will have a certain wavelength, or even what medium it travels through will have a certain wavelength. The product of those two values gives us the velocity or the speed of the wave. The amplitude of a wave is the amount of energy in the wave. So if we have a very large disturbance, so if again you're dropping a rock inside of a calm pool of water, and if I drop a pebble, I'll have a very small kind of initial disturbance, so there'll be a small amount of energy that transfers. If I drop an entire boulder, you'd imagine the water would kind of shoot up, and there would be a very large wave wave fronts that would develop. So it's that initial disturbance, or rather the amplitude of the wave is the amount of energy. And if we have an initial disturbance that transfers a lot of energy to the medium, then we would have a large amplitude. And the wavelength of the wave is also determined by the rate of vibration of the source. So just as the frequency, or as I'm kind of speaking something, or if somebody is singing, they can sing with different wavelengths to make different sounds, and it's the rate of vibration of their vocal cords that are causing that. So now we're going to move away from waves and talk a little bit about light. And some of these terms we're going to talk about also occur for other types of waves, that light-like waves. So light itself is a transverse wave, and this may these types of things we're going to look at, like reflection or propagation, occur for some other types of waves as well. So in many instances, light travels in straight lines. And if we have something that travels in a straight line, we call it rectilinear propagation or straight line propagation. And the word propagation, this isn't defined here, but you might want to write this down. Propagation is how energy is transmitted in a wave. So we're going to use that a bit, propagation. It's basically if we have light or even water waves, they're moving through a surface, how they move is called propagation. And light has a straight line propagation. The change in direction of a light ray after meeting an obstacle is called reflection. And the law of reflection, it's kind of shown below, so you might want to copy that image, states that the angle of incidence is equal to the angle of reflection. So in the image you see theta I, that's our incident angle, equals theta R, which is our reflecting angle. We also have the bending of light. That's known as refraction. And this occurs when light travels from one medium to another. So you see the image on the right. We have the incident ray and the reflected ray. So theta I equals theta R. But we'll also have this refracted ray, theta 2, that will be at some angle, but it's not necessarily related to theta I. And it's more related to the mediums, the change in the mediums. So when a light wave strikes a transparent material, some of the light is reflected from the surface. The rest of the light passes through the material. This is known as a partial reflection, partial refraction. We also have the separation of light. If it separates into spectral components, we call this dispersion. And this is typically demonstrated with a prism. So we have incident light, and the incident light, it consists of red and blue light in this case. The two different types of light have different wavelengths. The red light has a different wavelength than the blue light. So their refraction angle will be different. And when the light refracts at different angles, it disperses into its component colors, or its component parts. So we'll have that red light shown separately than the blue light. Here's a quick little question here. It says, two waves with equal speeds have frequencies that differ by a factor of 3. What is the ratio of their wavelengths? So if one wave has a speed that's v, and the other wave has the same speed, we'll call it v, but the frequencies are different. We would know that the wavelengths would be basically v over f. And it would be v over f1 and v over f2. So our f1 is equal to 3 times our f2. So the difference between these would be that our lambda 1 would be 1/3 of our lambda 2. I won't show you how this is done. It's rather simple. So you can try this out using the universal wave equation yourself. The next question is also quite simple, using the universal wave equation, but I will show you how to do this one. So we have a wave on a string. The frequency is 0.83 and has a wavelength of 0.56. So the product of those gives us our speed. So our speed is 0.4648. I won't round that at this point because this is just an intermediary answer. We're asked to determine the wavelength when a new wave of frequency 0.45 hertz is established on the string and the wave speed does not change. So if this is the same speed, we know that v equals f lambda. So lambda would be v over f. So if I just divide this by 0.45, I get my answer, which is 1.03. And I only have 2 significant digits, so I round to 1.0 meters. So that's it for this lecture. This is a bit of a review, as I mentioned. So please try the work out, and there is a spot on the website in the discussion board area for you to ask and get your questions answered for Unit 4. So if you have any questions, you can use that.